about the prognosis using Bayesian updating. In our prognosis work here, we try to estimate the parameters of the damage growth model, where the theta is related to the damage or the indication of damage. So we want to estimate the probability of the theta given the measurement or the NDE data. Well, as we learned in the morning, based on the Bayes theory, the posterior probability will be proportional to the multiplication of the likelihood probability of x given theta, which is a conditional density function of probability of the measurement data given the parameters times the prior probability f of theta. So what we are doing here in the Bayesian updating is every step when we have the posterior probability updated, which is a probability of theta, right? Given the new data x every time we have a new NDE measurement. So this posterior probability will be used as the prior probability on the right-hand side of the equation in the next updating step. So everything becomes recursive, and you will update the posterior probability when you have new data coming in at each step. The prediction error, in this case, since we are predicting the future theta, right, the damage model parameters when we're having new data coming in. So the prediction error is defined based on the theta, and you can look at the expected value of estimated theta minus the two values theta, and you can look at the expected theta minus 2 theta square, based on the definition of expectation. You can calculate the prediction error using this formula, and the error is minimized when the estimated theta is the same as the mean of the posterior distribution or expected theta given x. One method to do the Bayesian updating is the particle filtering, and you'll see we are actually using Monte Carlo simulation here to generate or to populate the probability when we are doing the updating resampling based on the likelihood probability there. So that's why this method is also called sequential Monte Carlo method in some literature. So the basic idea is to incorporate the measurement uncertainties that we discussed before and the nonlinearity into the Bayesian updating by incorporating the Monte Carlo simulation and resampling stage of the probability function of x given theta. And here we have a little bit different notation here where z is the x in previous slide corresponding to the new data coming in. And the unknown parameters theta and the condition density model as a swarm of particles instead of a single deterministic value. That's how the Monte Carlo simulation will play a role here. and each particle here is corresponding to a probability value. And the variance of this swarm distribution reflecting stochastic nature of the damage growth in uncertain environments or with uncertainties. And if you look at this chart, the updating from k-1 step to k step to k+1 step is when we have the previous posterior probability in k-1 step. This is the left-hand side of the equation, probability of theta given z, or the previous equation f of theta given x. That you use that to update your prior probability, right? So probability of theta, now in k step, you just replace the prior probability on the right-hand side of the equation with this posterior probability. And well, this is related to the damage, right? You can use this prior probability, pass that into the damage propagation model. So you'll have a damage model for different damage problem you're working on. And in the next example, you'll see we'll adopt the Paris law for the damage propagation model, and we also developed a new Paris law for the composites damage growth. Well, from this prior knowledge, we can update the prior knowledge based on the damage propagation model. I'm sorry. So you can now use that damage propagation model outputs and try to calculate the likelihood, right? So likelihood, based on what I explained yesterday, is nothing but a data-driven approach. When you have data, you can have your likelihood, which is a probability based on the given parameters, and you can get the data, and then you can using data approach to fit and get the likelihood, right? And using particles here is you are going to keep the particles with higher probability, while discard the particles with lower probability, and make a duplication, try to estimate the new posterior probability of theta given z. And pay attention to the notation z here, that you are considering the measurement now up to k step in this resampling and updating step. With that, you can go to your next step. The updated posterior becomes the prior probability in the k+1 step, and you will keep this moving forward. Well, a couple of things that we need to consider, and what our contribution and what I want to teach in this lecture is, on top of the particle filtering, that we will integrate the multisensory and the measurement into our particle filtering iteration. For multisensory ND measurement, in this case, we try to estimate the stiffness of the composites. So if the true stiffness parameter AI of structures known, then evidence from individual NDE techniques where we label them as Z1, Z2 to Zm, let's say we have M measurements, then they can be considered to be statistically, independent according to Bayesian networks. Well, we have this assumption that they are independent to each other. This will bring a simplification in our calculation. particularly for the joint likelihood probability. Let's look at this likelihood function, L of Z1 to Zm given the AKI. So for K step, by given the stiffness parameter A, the joint likelihood function of this M and the measurement from multiple sensors that by assuming they are independent of each other, right, we can rewrite this joint probability into the multiplication of each individual probability. Well, each of them, Z1, Z2 to Zm, coming from different NDE methods. Okay, and you will assume that the individual feature from each NDE method or NDE data here, they are different, and the feature characterizes as same parameters AI also be different, and they're independent of each other. And this will make our calculation much simpler. Well, you can also put a question mark here to test the validity of this assumption, whether this is true or not. Well, for some cases, that you have to be careful that, okay, if this is independence assumption is true. Well, let's assume this is true, and we can move this forward and try to validate this using experimental work. So the work is carefully designed using a fatigue test. Well, definition of fatigue, although we talked about fatigue already, in this case, when we study the fatigue in composites, we have this sample subject to a cyclic loading and progressive localized permanent structural change in material subject to stresses and strain over a long period of time. That is one definition of a fatigue. And it's progressing at a lower rate and introduce local matrix cracking in composites, and you'll see delamination in the material. This delamination will be characterized using NDE methods. We introduce different methods in day one that are capable of imaging these composite samples. Right. So I think the previous lectures prepared the underlying physics and how we can image those samples. Now assume we can do that, how we can take advantage of the NDE measurement and use what we just learned in prognosis to estimate the damage growth over time. Everything's done in the CVRC at MSU. And here's a picture of the experimental setup on the MTS machine for the tension fatigue test. We introduced an open hole on this GFRP coupon, so the damage will be more easily to initiate. Otherwise, it'll take much longer time to fail this sample. And we followed ASTM standard D5528 with the applied load to be 70% of a failure load with load ratio 0.1 and fatigue test frequency at 3 Hertz. We will have the true stiffness measured from the MTS machine. These are not coming from our NDE methods. These are just from the MTS machine. We can get them measured, and we can use this as a ground truth or the true stiffness overloading cycles. And you can see a starting point and a failure point after a number of cycles. Before we validate our multisensory NDE and monitoring of damage growth, we have to come up with a damage model. Previously, we don't have a damage model for composites, or there are a very limited number of composite damage model, I would say that. And based on the data we got, we realized for this type of composites and the delamination growth over fatigue cycles, that it follows a model we called Paris model. Take a step back. If you're working in the metal fatigue problem, and when you're looking at the damage growth in metals, Paris model is well known, which is an exponential it's a power law model where you can see the damage growth over time, which can be mathematically modeled as a constant times the stress concentration to the power of m. And I believe we've seen this in the last day lecture. Remember, we have 6 to 8 samples, and we look at the damage growth over time. Well, for the composite damage growth, we observe that it's actually going to be 2 Paris curve. The reason for that is the damage growth, in this case, the delamination growth over time is not going to be just describing one set of parameters, but it's going to grow much faster in region number 1. Then you're going to have a transition point associated with a transition energy there. Then it grows much slower after that. Well, in physics, one explanation for it is due to the complex damage in sequential phases. And this is accompanied for the non-uniform stiffness degradation in this layer structure. So in region number 1, you have matrix cracking at the initial stage. On the left, region 1 here. Then you have delamination growth during midlife and fiber breakage near the end of life. Okay, so with that knowledge, so we can develop a model. Now we have 2 set of parameters, M1, C1, M2, C2, to describe the growth of this damage, a K at the K step. So for Tk less than this T star, this transition or jump time, that you will use C1, M1 to describe the damage growth. When after that, similarly, you have C2, M2. Another unknown parameter to estimate is the T star. So the total problem becomes the estimation of theta, the parameters, right? Theta, which is M1, C1, M2, C2, and T star. Okay. Now, let me introduce different NDE sensing methods. For your own practice of multisensory NDE sensory data-based prognosis, and you can choose the NDE methods that work for your own problem. But the principle here I taught is going to be the same. Well, our NDE method for this GFRP damage growth problem, we start with OTS as I discussed yesterday. The sample is transparent for OTS. In this case, then you can use this ballistic measurement to evaluate the damage, and you can see those subsurface details. The theory of this OTS can be found in a paper we published in 2016 on the composites part B. This technique is sensitive to manufacturing defects and also in service defects. And it gives you a rapid non-contact high resolution and low cost measurement. This shows you the data at different loading cycles, starting from healthy sample, the pristine one with a hole. Then you can see at different cycles until it reached to the total failure cycle around 1382, and you can see clearly the progression of damage from A to J. Well, from the OTS data using image processing, as I said, we will not spend time on learning the generalized or the data processing in general, like the segmentation. Here, what we used to segment the damage area. Then we use thresholding and so on to find the damage area. Well, assume that is basic knowledges you learn from signal processing class. That you can calculate the delamination area versus the low cycles. Now you can find the damage area from OTS. You can clearly see the smaller value here. You can see those greenish or yellowish region until reach to the failure, those green, yellow, and red region, and it's increasing over load cycles. And you can find the correlation between normalized stiffness from MTS measurement and the damage area from OTS images. Right, so you can find this correlation by plotting the stiffness versus the damage area from OTS. Right, so this you'll have a good correlation and with a second degree polynomial fit. Okay, now let's test using single NDE method, pair OTS, to do the prognosis. The steps of doing prognosis is you have the OTS measurement. You calculate the stiffness from the OTS stiffness correlation curve, which you obtained before, and predict the stiffness using the particle filtering based on the new stiffness data coming from OTS, right? So you'll have the previous measurement, like green dots here, and you get the stiffness calculation from the correlation curve you obtained before. That is your prior knowledge. And with new data coming in, you can predict the future stiffness, which are related to the damage state of this composite sample using the prediction particle filtering predictor, and you can calculate the remaining useful life. All right, so there's one map here which show that how we can do the correlation, and the correlation curve you can obtain from previous measurement. give you the prior knowledge of it. And the likely computation step in particle filtering is showing here. As you can see, you can use the OTS measurement and try to find the likelihood probability. In this case, you'll see we adopt a simple Gaussian model here. So this is a simple Gaussian model. From these two figures, we can see the performance of the prediction. Statistically, we can look at the median. We can look at the upper, lower boundary here of the estimation. Well, the two stiffness is given by the MTS over time. So you can see when we have OTS measurement, then we can predict the future stiffness based on previous value. And if you look at this in terms of the remaining useful life, 2 remaining useful life is given. We know the ground truth from MTS measurement. Then we have the estimated median RUL and mean RUL over time. You can clearly see that when we have less number of data, the estimated error is large, and we always have a underestimation here. Then when we have more and more data coming in, then it becomes more and more accurate. And for the confidence bound, here we choose 90% confidence bound. You can see the confidence is increased over time, or in other words, the bounds becomes closer and closer to the true value. Right? So previously, when we have less number of data points, because of the uncertainty in the model, that we have model uncertainty here, that our prediction or the RUL calculation is off. As I said, it is significantly underestimated. But when we have more data, the uncertainty will be reduced. Okay, so we actually achieved the prediction based on one ND method. Now we try to select the second ND sensor to do the prediction. This is based on the guided wave sensing. This just a preview of tomorrow's lecture. It will mainly on the guided wave, NDE. So you can see the lecture notes I developed for this course, is following a logical path here. We start from the fundamentals. Then I will talk about the UQ examples based on the fundamentals. Then we'll make changes, shift to the prediction by also introducing new ND methods. Then tomorrow you'll see the guided wave-based SHM. So one suggestion for you is when we have a new concept coming in, I hope you can understand the materials and do some extra reading if possible. I know this is a very intense course in 5 days, but if you can do some additional reading, which will help you in the next day's lectures. Well, anyway, for a guided wave, this is one type of ultrasonics testing, ultrasonic method, where basically you'll observe the ultrasonic waves using here the transmitter and receiver pair. Those are PZT patches. The setup here is you have a network of PZT sensors, and you can monitor the guided waves transmitting from one here, a transmitter, to another sensor, which is a receiver here. If you zoom into this sensor setup, then there's a clever design here where you use a double sticky film in between the PVD sensor and also the sample. Then you make this flexible skin. So this we call the pressure sensitive adhesive that you can attach this PVD skin to the surface of the sample. Using the transmitter, you can have a generator to generate a Gaussian pulse and excite that, propagated in the sample, and received by a receiver. Well, in comparison to the permanently bounded transducers, these sensing skins are reusable. So you can actually attach and detach it. And also the distance between the transducers are held constant in respective to any plastic or permanent strain in the specimen. This is one parameter setting for the measurement. The peak voltage is 10 volts here. The frequency we use here is 50 kilohertz. And tomorrow we'll see how we choose the optimal frequency when we do this measurement. The typical signal is showing here, and with the excitation in red, you will measure the receiver signal, and you'll see two modes here, the symmetric and asymmetric mode. And due to the dispersion and the wave velocity are going to be different, and you can clearly identify different wave modes and calculate the time of flight. By adopting the time of flight as a signal feature, and you can use the time of flight changes to study the damage state in the sample. Okay, the same fatigue loading, and you can have the PDD transducers attached, or now using this sensor skin, reusable sensor skin, to monitor that in real time. One advantage of using this OTS and guided wave sensing is everything can be done in situ. In situ means that this can be done in line and in real time. So you can have this damage monitoring when you're doing the fatigue loading cycles. This clearly shows the TOF difference between the peaks of received excited signals when you have the damage progress in the sample at different cycles. With that, you can calculate the TOF changes, delta TOF, versus load cycles. Well, if you recall what we did for the damage delamination area from OTS, you have a very similar pattern here. And you can also calculate correlation between the normalized stiffness from MTS machine versus a delta TOF from the guided wave data. Similar approach, what we see from here is instead of using NDE sensor 1, now you have NDE sensor 2. Here is a measure data given by the guided wave. Everything else stay the same. You can have another way of estimating the stiffness and also the remaining useful life based on what we calculated from the damage state. Right. So now with these two calculated, one way of doing the fusion is, okay, now we say we have both measure ND measurement from guided wave. You also have ND measurement from OTS? Well, we can just simply using average, right? This is a very intuitive way that I have two ND measurement. Well, let's do it. So I have those two data. I just simply do the average here, add them divided by 2, and use this as my average measurement. And then I can do the prediction. Well, I can predict the damage loss in it. And the RUL prediction is more accurate than using one sensor data, either Galloway or OTS. If you look at the RUL here, RUL estimation here. Well, not bad, right? Not bad. But is this the right way to do it? Always ask yourself that, wait, why you just add them and divide by 2? In other words, you give them the same weight, right? You give Galloway and OTS 0.5 weight. Is that true? What is the physics behind that? Well, probably your answer, no, there's no real physics behind it. I just think that averaging is the right way to fuse it. Then why don't you choose 0.7, 0.3? Right? That's something that very difficult to justify about doing this averaging, or why it is not a weighted averaging. Well, we think it's better, or it is a correct way to consider this data from guided wave and OTS in the framework of joint likelihood. Instead of using averaging, that you should have a joint likelihood calculated to give you the conditional, by the assumption of conditional independence in Bayesian network. So for each method, you can calculate the likelihood now. You did that before. And we multiply this likelihood to get you the joint likelihood for the fusion data set. But this is different from adding the NDE data and divide that by 2. Even we are working at a feature space, adding the feature from 2 different methods, assigning a weight there is not making a lot of sense. Although the estimation of the RUL here, although the prediction accuracy might be better, but it's very hard to explain physics. Well, we now put everything into this Bayesian network and using the joint likelihood as the multiplication of each individual one with the independence assumption, we can use that joint likelihood in our prediction. You can see this from our prediction here. You predict the stiffness using particle filtering, and also you can see that with more and more measurement here, where we have 4 or 5 measurements from both NDE methods, we already have a very good remaining useful life estimation. And the number is within 20% of the 2 RUL. This clearly outperforms the previous predictions by either individual method or the average data, which I just mentioned does not have a very good physical ground to do the simple averaging. Okay, so this shows the framework of doing prognosis. We demonstrate using individual NDE data, average NDE data, and fused NDE data using the joint likelihood approach. And the performance can be quantitatively assessed, and it clearly show the advantage of using this data fusion. This is another way of looking at the prediction error. And we can see the blue curve here, the joint likelihood, outperforms the other methods. Well, the average here is accidentally better than individual, but this is not always true. If we don't have the fully understanding what we're doing here, sometimes we cannot guarantee the average is better than each individual ones. Okay, so here comes the summary of the ND prognosis here, that we find to complement ND measurement. And we also can realize that in real time, inline or in situ ND measurement to make this as a monitoring technique for damage growth under fatigue for composites. For different materials, in this case, a complex composite, that we need to develop a good damage growth model. In order to estimate the damage growth model parameters theta, a Bayesian updating scheme is proposed that we can use the new data, get the new data coming from any measurements to update the estimation of a posterior probability over time. There are different ways of doing it. One way of doing it is using the particle filtering to statistically estimate the posterior probability. Everything will be assessed using quantitative metrics, and we show that by doing the fusion of NDE methods. Here is a joint likelihood approach that you can have promising results by using two sensors at the same time. Think about using more sensors, then you can further improve the prediction accuracy or the performance of your prognosis algorithms. Some future work being identified here. For example, the empirical correlation curves between NDE features and structural stiffness should be replaced with physics-based model. Then if you have a better physics-based model, then you don't really need to rely on this empirical correlation. By assuming that you can get, for example, the juice stiffness measured by the MTS machine. Then Paris model here should be further investigated for different loading conditions. And another question here is for the Paris model, how to determine this transition time or jump time based on the understanding of the damage or the failure mechanisms in the complex material. This is important. Okay, so let's revisit a slide that I gave in 2016. I want to use this to conclude some of the work we discussed here. That a complex system, complex structure, complex materials, it is damaged or degraded over time. You can have a test-based approach, and you can have sensing imaging done. This is what has been covered in course 1 and the first half of this course 2, based on different physics and based on the different imaging method, that you can get multi-scale information, multi-model information, and multi-spectral information. Well, all this information can pass it to the cloud computing or distributed computing using data engineering, then oh no, I go this too far. Let me okay. Then with this data and data processing that we learned so far, you can have a data-driven or physics-based or physics model-based prediction of what's going on there. For the sensing imaging, with those sensing imaging capability, that it's possible to achieve, for example, in the additive manufacturing, we can have a better understanding during the manufacturing stage, and hopefully the material or the structures will have the self-diagnosis capability using those sensing imaging information. Well, for the other branch, where we have the prediction capability, you are developing the self-awareness of the system through, for example, inline decision making. And with self-diagnosis and self-awareness, those are the key attributes of a smart system, right? Just like a human body, that we can have our self-diagnosis and self-awareness capability to make decision making. Another branch I want to point out here is we should consider the environment conditions. So consider the probability failure based study and incorporate environment condition. And with the discussion we had so far, probably we should add one more branch here, that we should infer or try to understand the associated uncertainties, not just coming from the environment, but coming from more uncertainty sources. And this will help us to do a better inline decision making. The top half from the diagnosis part is small diagnosis, because you have the self-diagnosis capability, while the bottom one is a intelligent prognosis arm, that you have a self-awareness of the system. And this combination will give you the next generation of NDE or SHM. And hopefully I will conclude this lecture on day 5 by presenting what I think is the new paradigm in the through an introduction of the concept of ND 4.0 and 5.0. Okay, so that's the last slide of my second part of today's lecture. And I'll stop here before I move to the lab session and case study. I'll start with this miniaturized ND sensing system with data processing assisted by deep learning. I have some video to play, although it's a draft video, and also we will have this project as a example of showing what we have learned so far in data processing and deep learning based damage identification and classification. So I'll stop here if you have any questions. Any questions?
Yeah, let's check it once. Any questions from the audience? Anyway, this lab session, the recording is not allowed for that.
Because I'm going to share another lab session, but for the case study, I'm going to share some videos, which I don't think we should, because everything gonna be live on YouTube or recorded, right?
Yeah.
So I think I need permission to make that publicized. But
Okay.
for
So
small
yeah.
audience, I think I can show that just within the class.
So I'll do one thing. I'll bring my technical person. I'll ask him to stop streaming it on YouTube and and not to record to this portion of the video.
Yeah, that would be great. Thank you so much.
Yeah. So just give me a few minutes. You take a break.
Okay,
I'll just arrange these settings that we don't record it.
okay.
Just give me 2 minutes.
Yeah, I'll stop sharing and I will start sharing the other one.
Yeah. Uh, Hello. Uh, is there anyone from IIT KGP, the GIAN portal?
So when we're setting this up, if there are any questions about the lecture, feel free to ask. I will be very happy to address that.
Yeah, I'll ask. Yeah, any questions from your side? Hello. Is there anyone from the IIT KGP side, from the GIAN portal.
Uh, I think if we can just stop recording, I think that's fine. And if it is even live, that's okay.